So, welcome back, geometers. I do want to stress, there was no homework. Boo. But worry not, we'll get some today. And we'll have to do a little bit of work before we get the assignment, though. Aww. I love this, just for the record. I'm going to get like 40 of them. And we're just going to, yeah. Existential dread is the next one that's coming. All right.
How'd you do that?
I don't know. Something uncomfortable, cringy noise. Anyway, here's what I want us to do. Today, I'm going to use this foregone over and over and over, just so you guys are aware. Okay. Yesterday, we started looking at the opposite direction. Now, for this, we're going to prove these. And we're not going to do all the proofs today, but we are going to do several of them. So, what I want you guys to do, we're jumping in, and I can't really walk around because my microphone that I walk with is charging. But we have a foregone in front of us. I want us to, from this theorem, we need to prove it. And need to, from a mathematical perspective, yes. Want to, from an individual perspective, of course. But we are going to prove this. And all four or three, however many proofs we do today, I'm going to use QUAD. So it's going to be the same one over and over. Give me a second, or I'll give you a second. I want you to sketch this, and then I'm going to give you guys 60 seconds, which means I need the red hourglass if it is sitting anywhere. I will find it. It's over here. Okay, 60 seconds. I want you guys, all that I'm asking, not to do the whole proof, but over the next 60 seconds, once I pause this, I want you guys to find out what is it exactly that we're trying to show, and what are we given from this theorem. That's it. Find me what it is that we're trying to prove. We're trying to prove this theorem, but I need a statement that says show exactly this, and then tell me what the given information is from this theorem. 60 seconds. We'll come back together. I imagine some people will be able to do all of it. Some people will struggle. It's okay, wherever you're at. We're going to do it together in the end, but I want to see where you're at while I'm doing attendance. So, talk it out. And it doesn't really matter, but whatever we write as our show statement has to be the last line of our proof, right? So, two obvious options, I think, or one obvious and one less obvious. First one, how many of you guys just had the gut feeling that I'm just going to write show QUAD is a parallelogram? It's possible, right? Like we can write that. That's what we're literally trying to prove. But what does it really mean to be a parallelogram? So we could say show it's a parallelogram, or if we don't want to have to add that last line, what would UA need to be parallel to? Or sorry, congruent to rather. Wait, if they're opposite then. Okay, so it has to be parallel. Thank you. QD. And any other? UQ to DA or AD, whichever way you want it to go. Okay, whether we're saying show this is a parallelogram or we're saying show these, they're the same thing. Because by definition, if these are parallel and these are parallel, then it's a parallelogram. So we would be there. Okay, the other part of it from this, we always begin with our given statements. So like the things that we know is true. Now, I can see them in this because notice our conclusion, it's a parallelogram. That's the same as this statement. What is the if part of it? What do we know about this already? So it is a foregone, and I know some other stuff. If I say opposite sides are congruent, help me write those down. UQ is congruent to what? AD, and the second that I write it here, I'm going to mark it here. I now know those are congruent. Anything else that we're given? We also know that it must be the case that UA, the top of it, is congruent to QD. This is our given information. Now, in this part, I'm not going to make you guys do this on your own. What's easier to think about than a foregone now? Because we've only been doing foregons for a couple sections. Tregons. Can I make tregons show up in this? Yes. How? I'm going to make a diagonal. Does it matter which one? No. Chelsea, which diagonal am I going to draw? I'm going to draw one of the two diagonals, and I don't really care which one. Which one would you like to work with? Yes. So just to be very, to make sure, when I say diagonal, do you know what I'm asking for? Yeah, so it doesn't necessarily have to be slanted, which is what diagonal means. But if I turn this thing, then the diagonals would be like this. I'm just looking from one vertex to the opposite vertex. Perfect. I'm going to add a Q in. Now, when I add this into my picture, did it change anything about this parallelogram? Or what we'll hope is a parallelogram? No. So we could write it as we want to. I'm not going to write it. You remember what we call the extra lines that make us make sense or help us make sense? Auxiliary, which it's a very specific, it's not an oxymoron. Okay, so there's one thing that I forgot to mark on this. I wrote it, but I didn't mark it. So I haven't written that, so I can't mark it, but I did write those. Okay, now right off the bat, Liam said QA is congruent to QA. Now, I don't know if Liam has like the whole way through this proof thought out, or if he just looked and he said, that's something obviously true. It doesn't matter because I like it in either situation. Do we all agree that QA is congruent to itself? Why might I use it? Like, how could I possibly use QA congruent to itself? If I can show the triangles are congruent, we're probably about where we need to be. And we're going to have to get an old idea. But let's do that. Since it's a good thought, I like it, I'm going to include that. On step B, I'm just going to make that statement. And I know it always seems odd, but QA is indeed congruent to QA. And it seems silly to write, but by marking this, we have a way through this problem that was not there a minute ago. Klein, how do I know that's true? How well did Henning whisper it is the question at hand here. Because I saw this, I just didn't hear the rest of it. There it is, the reflexive property. Awesome. Okay. So somebody already suggested that the reason I might do this is because I can now show these triangles are congruent. Why would I want to show the triangles? But I already know the sentence. Oh, it does show me some angles that are the same. Now, we should make sense of which angles those are. And third hour, when I did this proof with them, we used numbers. We're going to avoid it today because it really did not make it easier at this one time. And we're going to see that here in a second. Jonah, I don't care which triangle you give me. Give me the name of either of these two triangles using the points on it. QUA, qua. Triangle QUA is one of those two triangles. And I'm certain that it's congruent to another one. I'm going to give you guys like 10 seconds. Chat with your neighbors, 15 seconds. I'm going to call somebody random. Which other triangle must it be? Why? Okay, so that's fair. We'll talk like outside of here, but I do want to just catch you up. When we put the marks in the triangle. And if that's totally okay, just so you know. So we'll get to we'll get you there. Don't worry. Although those marks mean is that they're the same. So if it has one dash across it, we know right now that it's the exact same length as that's all those marks are. Just like these doubles, the 2 dash and the 2 dash, mean that these are the exact same length. Now, when we're looking at this, if I went from QD to A, I go across 1 dash and then 2 dashes in that order, right? Like if I start at Q, because that's where I wrote first, I go from Q to U, which is across this 1 dash, and then U to A, across 2 dashes. Do you agree? Like when I write, if I go from Q to U to A, it goes across 1 and 2. How do I go across 1 then 2 and 3? So, but if I go QT, I cross 2 first, right? How do I cross 1 first? All right, check it out. Once we match here and we see this. Did that turn off for a second? It didn't stop my recording though, so that's pretty sweet. All right, Sophia, we go from Q to U to A just like this, across 1 dash and then across 2. What is that the same as doing on the other triangle? A to D to Q, and we have it. Okay. Why do I know these two triangles are the exact same? Not CPCTC. Side, side, side? I'm okay with that. Side, side, side. Okay. So now here's the part where I'm going to avoid the letters instead, or the numbers, because the letters, I know they're ugly, but it's going to make way more sense to think about. Well, what matches up with angle QUA? QUA matches with ADQ. Do we agree that these angles have to be the same? And I can include it if I want to, but maybe we don't need them. I'm going to try these angles. What's the same as QAU? QAU. AQD. So that'd be A to Q to D. What we just worked out through this corresponding parts idea is that this is the same as this. Do you guys agree with that statement?
Yes. How come it's not that O in it?
Cool. So, big moment coming up. You guys remember everything about chapter 2 and 3? That's fair. I'm going to say angle. We just wrote this one. How do you want me to name this angle? I can't call it Q. That's not clear. I'm not going to call it a number either. U is up here. U to where? Q to A. Now, I know that normally we do just use the numbers, but there's a reason that I'm not using them here. It's harder to pick it out and keep it straight. This other one, I'm just going to name it DAQ. D angle DAQ. Okay. Is there another pair of angles that you guarantee are congruent here in the same area? AQD. Does this have an angle that we know it's congruent to somewhere? AQD. So AQD should be QAU, which would be Q to A. It'd be up here. Now, this is a super important part. I'm not even going to use those other angles. We could have written them, but they wouldn't have done anything for us. So let's see. We said QAU. We're going to get there in like 30 seconds. So yes is the short answer, just so you know. AQD. How do I know that those were the same? Love it. CPCTC. Follow-up question. What do these letters stand for? C, P, C, T, and C. The corresponding parts, so where they line up together, of two congruent triangles wind up being congruent. If they're the same shape, same size, when they overlap, of course, the angles are the same and the same. Okay, with this in mind, we're going to throw back an old idea. Now, I really wish that I'd done 6.3 and 6.4 together so we could just have all the theorems as if and only ifs. That would have been ideal. What? There's like 4 different groups of people smiling. Either you're smiling about different stuff or I have something all over my face. Bummer. Is that true?
Yeah.
How'd you break Klein's nose?
You rammed into it.
Oh, bummer. Okay. That sucks. Lost my train of thought. Okay. If I have these lines, and I don't want you to draw this, I just want to think about it. And if I have these lines, if these are parallel, then alternate interiors are congruent, right? Yeah. What if I don't say they're parallel? What if I just give you this and say, hey, these are congruent? You conclude these lines are parallel. It's a converse of it. It goes both directions. Now, the fact that we can say if they're parallel, then these are the same, but we can also say if these are the same, then they're parallel is the magic to this idea here. Check it out. If I look just at these red ones, those are interior angles, except these, I believe, being cut by a single transversal. That's exactly the picture here. I'm going to make it obnoxious up here. You don't have to do it on yours. But what we see on the board right now is that these two lines, if I cut them with a single one here, I get alternate interior angles being congruent. What must we conclude about those two lines initially? They must have been parallel. There's no other option. So by that little observation on E, too bold, on E, we are already at the point where we can say with confidence that UA is parallel to QD. It has to be that way. UA has to be not congruent, but parallel to QD. Why? What is this angle pair known as? Good. It's the alternate interior angle converse. I have no issue if we just say it's alternate interior angles. Like, I'm good with that. if I wanted to obnoxiously do the same thing here, and I said, check it out, here is a line, and here's another line, and here's a single line that transverses both of them, or it has a transversal. Do we have between these lines any angles that are the same? Like that is the same as this, right? And they're on the same or alternate sides of that transversal. Are they on the interior between the lines that might be parallel or outside of them? They're interior, right? Everything here is between them, which is what we'd call the interior. So what else do I know is parallel then? Guaranteed. UQ, same thing. UQ must, what? I'm going to call it, say, QU here. Must be parallel to AD. And for the same justification, right? Now, this is why I asked that question at the start. Do we really just want to say prove their parallelogram, or can we just prove this? Does this mean it's a parallelogram? Did we just show that that has to be true? So what must this be? One more time. It is a parallelogram, which is exactly what we were hoping to show. And look at that. We are proven, without a doubt. If you ever give me a foregone and you tell me opposite sides are congruent, every time it must be a parallelogram. So we get this converse statement for free. Not for free, it was a little bit of work. Okay. Doable? Okay. Let's do another proof. Then you go to A1. For sure. But if you're going to have a proof that takes 27 steps, it's probably not going to be a 2-column proof, just for the record. Like, no, it'd be neither of those. It would just be written out. So eventually, and this is just a fun thing, I'll show you guys proofs. I'll show you a bunch of proofs. This is out of a random book. So this is the proof of calculus is what this class is. So here's a theorem, and they say a bunch of fancy stuff. Here's their proof. It's this. This is their proof. It just says, look at this like paragraph of writing. This is what they turn into. 2-column is nice because they justify. They justify in here too. If we take phi of t to be t squared, then this theorem shows that f squared is in the reals, like, and it's all sorts of crazy stuff. But this is what proof turns into. No more 2-column. Clearly. Sweet. All right. This book is called Baby Rudin. It is a very, very well-known book in mathematical analysis. Let's do another proof. Cool. So right now, just from memory, I want to see how many of these we can get out. I did not call this a name. If we want a name for it, these are converses. I like the way the old book wrote these. Instead of saying, like your book here, just so you guys know, this defines this theorem as the converse of theorem 6.7. I'm not going to call this the theorem of, or the converse of that. This is 6.11. We're going to call this test 1 for parallelograms. Because all of the theorems that we're going to get out today are just ways for us to see if something is a parallelogram or not. Let's just say they're all parallelogram tests. Here's how we figure out if it really is. So what I want us to try to do from memory is, let's see how many of these important things about parallelograms that we can recall. If it's a parallelogram, then opposite sides are congruent, and then we turns around. If opposite sides are congruent, it's a parallelogram. We've done that one. What else do you know if it's a parallelogram? Any special relationships? Cool. So what's the converse of saying if opposite angles are congruent? Dang it. What's the converse of if it's a parallelogram, opposite angles are congruent? Boom, we have it. So our first theorem was test 1. Let's call this one test 2. So one more theorem real quick. 6.12. Your book says this is the converse of 6.8. I'm not going to call it that. I'm going to call this test 2. And you will never hear me reference these again. I just like to give it some sort of name. And because these are just testing for parallelograms, this seems appropriate. Okay. We're going to write this one a little bit differently. I don't know that we'll prove this one because I think the proof will be about the same in the end. But let's check this out. Your orders are going to be different. And that's okay. So if opposite angles of a foregone are congruent, what do you think that foregone must be? Yeah, seems reasonable. We said if it's a parallelogram, then opposite angles are congruent. We're just turning it around. If the opposite angles are congruent, then parallelogram. Now, for this theorem, and I think just this theorem today, I don't want to prove it. And the only reason I don't want to prove it is because if we started with this, I bet we could do something very, very, very similar to what we just did a second ago. Cool. Okay, we're not going to prove this one. We could work through the proof pretty much the same way. But now we have two of them. If I give you a foregone and opposite sides are congruent, you now know without a doubt it is a what? Parallelogram. What if I give you a foregone and the opposite angles are congruent? Parallelogram. Are squares parallelograms?
Yes.
Yeah. Each angle on a square, opposite angles are both 90, right? It fits that. It is a parallelogram. Okay. So another one that we get, and you guys are going to prove this one for me, and I'm going to help you set it up. And my orders are weird. This is 13 now. Theorem 6.13. And we'll just call this test 3. Bless you. If you have a parallelogram, what do you know about any consecutive angles? Which means just if I start at one angle and I add the next angle to it. Every time. Doesn't matter if, and just to really highlight this, and we'll get the picture because we're going to use that same one. Okay. Here's that same parallelogram for here in a second. And I'll do it over here so we can write the theorem first. If, and I got to think of how I want to word this. If an angle of a foregone is supplementary, which just in case. Supplementary is a really specific client. Only call on you because I can see you're very clearly looking at somebody and mouthing some words. What does it mean to be supplementary? Hold on, let me find it. I'm going to give you a hint. All right, if you're at a loss for it, you need a hint. What comes first, 90 or 180? Okay, so there's two special words that we see all the time, complement and supplement, or complementary and supplementary. What comes first alphabetically? So complement lines up with 90. What do you think we're going to do supplementary must be then? You have it. I think you're just getting frazzled by speaking. What was the other special number? 90 and? 180. It is 180. So if they're supplementary, just a reminder, this just means that the angles sum to 180 degrees. If an angle of a foregone is supplementary to both consecutive angles, what do we conclude about that foregone, do you think? Then it's a parallelogram. And we're going to do this problem. I would like very much to turn the game on as well, just for the record. So we'll see if we can work a little bit with the game on, and we'll take a pause so you can do a few problems. But let's check first. Consecutive. And I'm sorry, I'll try to write bigger still. It is so hard to fight that. Okay, first thing, what does it mean to be consecutive? I like continuous. That's a good way to think about it. But like, if I'm reading consecutive pages, each time I turn one, right? One away. So for this, just to speak to make sure that we have this, you don't have to mark it, but what is consecutive with angle Q? U is consecutive or D. And in either case, these have to be supplementary. Now, I want you guys to prove this, but I'm going to help you with this. Right now, we have angles are supplementary. Okay. I'm trying to decide how much I want to give you with it. I don't know what this is, but I know it's X, right? Okay. What might I call this one? I might call this Y. Now, I'm claiming that these are supplementary. And we can do a formal proof if we want, or we can do a logic proof. I'm going to let you guys talk. Like, I'm cool with either. If you need practice with the formal proof, we should probably write it out. If you just want to work on the logic part, we can just talk it out. Logic part here? Okay, so let's try to think about this. What do I know x plus y adds up to? 180. Which means what lines do we guarantee must be Parallel. These are now parallel. Because I know they're supplementary, that is parallel. Okay. Now, with just this, how do we get to the other side of it? Say that again? Ooh, you're assuming it's a parallelogram to show it's a parallelogram. Why does it have to add to 180 with y? So here's my challenge. You don't have to prove it. I want you to just find the next chain in the logic here. I'm going to give us about 60 seconds. I'm going to get my NFHS stuff logged in too while you're doing it. With your neighbors, try to come up with the next logical step that we can get there. Cool. I'll give you some time. It might be a little more than 60 seconds, but talk it out.